Gut, der erste Vortragende, den ich ankündigen darf, ist eben der Denny Yu. Ich habe ihn zuvor schon einige Male gesehen, da der Denny aus der University Purdue zu uns gekommen ist und der deutschen Sprache nicht mächtig ist, werde ich jetzt auf das Englische wechseln. Denny, where are you? Could you come forward? It's your time for your speech. All right, so just to give you a heads up, Denny is again the Fulbright professor, University of Purdue. He's already with us for a few weeks, and within these few weeks, we could already experience his expertise in a lot of different things. He already was a part of a lot of research meetings and gave us a clue about a lot of things that we had no clue about. So that is the fabulous thing about research exchange, about lecturers exchange, and about exchange in general, that you just get a lot of more knowledge that you otherwise wouldn't have. So thank you again, Denny, for being here, and the floor is yours. We're excited to hear what you have to say.
Yeah, I'll just, I could just do this. Did it work? All right. Well, good afternoon. First, I apologize. My German is very, very limited, so I have to present in English. So please bear with me for this presentation. Well, thank you, Professor Hollis, for the wonderful introduction, and thank you, everybody, for attending this seminar and hearing my talk on preventing musculoskeletal injuries in the workplace. As Professor Hollis mentioned, I'm a Fulbright professor here at MCI. Thank you all for such a warm welcome. But back home, I'm an associate professor in industrial engineering at Purdue University. But I also have appointments in health sciences and surgery, so I also work a lot in the surgery realms. In my spare time, in the summertime, we do a lot of work with the Air Force, and we also have appointments there. But before I talk too much about the research, just a couple quick introduction. What is Purdue, and where is that at? So Purdue, we're a university, a public university in the United States, located in Indiana. We are decently ranked in general, but where we specialize is engineering. So for engineering, Purdue University does pretty well. Here's the map of the United States, and obviously you guys can see what the next question is. Where is Purdue University? I'll give you a hint. Purdue University, it is located in the Midwest of the United States. So the United States is composed of various regions. It's in the Midwest. Now, if you took my hint seriously, you might be confused because Purdue is not in the Midwest. It's more in the Mideast, but that's more geopolitics, and that's not my area of research. But that's a quick introduction about Purdue. So some of the work that I focus on, I focus in more human factors and ergonomics. Specifically, I do a lot of work in figuring out what is the extent of human capability. When do they start being able to excel? And of course, when do they start running into problems? For this, I look at it in various different ways. First, how do we detect the limits of their physical capability? That's what we do in the more physical ergonomic side. Also, what's more interesting these days is what's happening cognitively in their brain. What is the limit on the brain? Specifically, we do a lot of work in surgery, so you could kind of think that it's very technically, cognitively taxing, in addition to physical. The other thing we work on is looking at the team. How do you understand the team performance and model that? Finally, the last part, which is the focus of today's presentation and talk, is interventions. How do we design interventions to make people perform or enhance their performance on the job? Here's kind of a quick preview of the exoskeletons that we've been experimenting with and applying in the workplace, specifically for surgeons. And I will give a little bit background on why look into ergonomics and exoskeletons first for surgeons, and hopefully we'll make some connections with some of the experts here today on potential applications and generalizations to sports rehabilitation and other domains. Before I get into the exoskeletons, I do want to also kind of very briefly talk about these other areas in the physical and cognitive areas that we work on in our research, just to give you an idea. For the physical side, and I think this is also more in the biomechanics, very relevant for sports, sports engineering and sports technology. Great. Currently, a lot of the state-of-the-art, we're using computer vision. So how people move, how quickly they move, and how much kind of biomechanical loads and stresses that's being exerted. That's what we're using we study their motion and biomechanics. How do we study it? We use computer vision or wearable sensors. Computer vision is basically using a camera, and then I get to detect where the body location is. In this kind of short loop video, you kind of see the person performing a lifting task, and then on the second one, you can see the computer vision overlay on it. One of the problems here is that this is the basic kind of open source. You can do it if you know a little bit of Python. You could try to do this on any camera video images you have within a couple of days. But the problem is you kind of see the skeleton. It's very wiggly and jiggly, basically very inaccurate. So one of the things that we're doing is that a couple things. It's kind of somewhat inaccurate, but it's also very limited. In areas like physical ergonomics and potentially in the sports, we're very interested in much more specific kind of measurements of their motion, not just the joints location, but also rotation, how body segments are orientated. So these are some of the things that we're working on, and how do you get even better and better analysis using computer vision. I also want to very briefly talk about some of the cognitive aspects of our work, because I'm going to try to fold it in a little bit later, is that we're very interested in seeing when people start breaking down cognitively, when things get so stressful that you're not able to perform at your maximum or your optimal state. You could think of it as like you're taking an examination. At an examination, you may say, hey, I know this, but at that moment, at that time, that pressure, you're not able to perform well. Situations like this, unfortunately, also happens very commonly in surgery. And you can imagine that you're getting, or somebody you know is getting a procedure, and your surgical team, they are at that stress level. Probably not the way they're not the state you want them to be performing at, because that's at a heightened stressful load. So what our team is doing is also we're developing sensor technologies to understand what's happening cognitively. So when the surgeon, or in this case our experimental, we're testing this in robotic surgery, is that when we detect when they're at a stress or high cognitively loaded state, how can we help the user? So here we use technology like EEG. That's the brain activity sensor, where you wear a hat and it tells what's going on inside the brain. We use a lot on eye tracking, which is a pair of glasses that tells us the eye patterns and eye movements. And what we do is that here we're able to show that we could stream this data in real time, understand the person's cognitive states continuously, and when we detect high load, we're able to do an intervention. We demonstrate this in robotic surgery. Everything's fake, simulated, not a real patient. But you can see here in this video, we're going to have a lot of blood in the area, fake blood, and makes it very difficult for the user to perform the task in the robot. So what happens is that you can see the chart here, is that when we see there's high cognitive load, you can see it's pretty low right now, but it's getting frustrated, they're not able to do it, and then once it gets high above the threshold, you can't really see it, but with reflection you can see this robot is automatically removing liquids from the field, so now exposing what the person needs to see. This is just an example of how you can take what's going on in real time cognitively of the user and feed it back into areas where we can make interventions, real-time adjustments, in this case, a robot removing fluids from the field. But enough about the background. I want to jump into the meat of today's talk is exoskeletons. As you kind of see, a lot of my work is focused on healthcare, but hopefully we could also, again, draw some conclusions and generalizations to other domains like rehabilitation and helping patients. So this is a stock image, a Google image, that when you search operating room, this is what you get. I want to see, like, based on your impressions, what kind of impressions do you think about in this environment, this workplace? I'm not going to make it too interactive because I don't think we have room mics, but from this picture, you could kind of get the impression that it's very calm, very serene, peaceful. People are at work, it's meticulous, it's organized, right? So this is what you get from stock images. But in reality, we're seeing a lot of literature showing that surgical work or performing this job is very hard, very challenging. Not just hard cognitively, technically, stressful-wise and time pressure, but also very hard physically. We see a lot of publications saying that, all right, given this kind of jobs and this position you're putting the surgeons and surgical team in, they are starting to get a lot of back pain, neck pain, shoulder injuries. So happens a lot and happening quite often. This is a concern because when you're thinking about industry jobs or working in an occupation versus patient focus, but in an occupational setting, people are going to work and they want to do their jobs. They don't think about themselves, especially true in healthcare. But now, due to advances in what we know in ergonomics and kind of occupational safety, we start to realize that these are problems that need new solutions, need new ways of eliminating that so our workers continue to perform their jobs safely. So here's some numbers. These are from the US, so it may be different in Europe. I think there are potentially cultural differences, but I see some head shaking, so maybe not. But chances are, if you talk to a surgeon or a healthcare provider like a nurse, chances are they'll tell you that during their career, they have probably experienced an injury or two. Back, neck, shoulders, very common. If it's not a debilitating or disability injury, it's at least very commonly reported they're feeling fatigue and pain after their jobs. In ergonomics, we know that there's very glaring reasons why people are experiencing injuries. Things like we call it awkward postures, but basically when you're doing a work in a position that's not optimal or comfortable, when you have to do a lot of repetitive movements or you have to use a lot of force. Now, the problem with this is that you could imagine that, again, going back to either you needing a procedure done or a close family member needing surgery, if your surgeon is experiencing some shoulder pain or hand pain, you probably don't want that person operating on you. And that's a problem because we see a lot of people are reporting that they experience pains and injuries. And then these pains, because it's such a I would say, a very safety critical task, very delicate task, once they do get injured, they have to stop performing, especially during disabilities. So big loss, surgeons spend dozens, 20, 30 years training. Patients, there's a very limited pool, and not being able to have that, not access to care, could be a huge problem. So let's give a quick introduction on the surgery and the surgical team. Because this audience is have a lot of sports experience, I don't want to make this analogy. I typically do, but since I have that analogy, I'm going to use it anyways, but with a little caveat. Surgeons kind of think of them as surgery is they think of it as a team sport. Obviously, it's not a sport. Terrible analogy, I know, but it kind of works in a way that everybody works together in order to make sure it's successful. In this team, we have the surgeon. We have it, these are just kind of representation from a Google image. That's typically the leader, the primary person. Then you have a lot of trainees or people that are training to become surgeons. They're surgeons. They got their medical degrees, and they're just specializing and learning more. And then you also have the nurses and technicians supporting this procedure all around the patient bedside. And here's some other images on where we're trying to think about where exoskeletons are coming in or why people are reporting getting injuries. Specifically here, we're looking at minimally invasive surgeries, but I kind of made a mistake here. I should not have the red circles. You guys were supposed to guess where the ergonomic problems are, but the animation did not work, so here's the ergonomic issues, the red circles. But basically, here in the red circles, you can kind of see some of those positions that the surgeons, the postures that the surgeons and surgical team need to perform in. Here in this picture, you can kind of see the surgeon having a tool. These are simulation, but they're having a tool and they have to operate with the hands lifted in long periods of time. A couple issues with that, so you can imagine that in a typical work, if your shoulder is feeling tired or you're sitting and you're constrained, you could just move around and shift positions or take a break. But you can imagine that, well, if you're performing a surgery on somebody, taking a break, moving around is typically not an issue, not a solution, because you're holding a blood vessel, an organ. You're not going to drop it and say, I'll be back in 15. I got to go take a break. Not an option. So that's why this is a potential issue in that they have to do it and they can't really kind of adjust themselves. Now, the person that we're showing here, that is typically the lead surgeon. And what I want to say here is that, if you look at the guy behind the surgeon, he's also kind of holding a device, also needing to hold that position. And I'll tell a little story about that. So as I said, the surgeon, they're typically, the leader, the boss. They get the best seat in the house, as in they can control where the patient is and where they want to stand. The assistant or the trainees, they unfortunately do not get the best seat in the house, and that's why you could kind of see the trainee in the behind, and kind of actually have to reach over. The problem with this, the second problem with this is that, so in this case, the surgeon is they're performing the procedure, but the trainee is actually playing a very key role. He is holding the camera. So you can imagine again, if the trainee kind of needs to take a break, drop the camera, they're probably not gonna be able to do that because, well, the surgeon is doing some maneuvers, could potentially be very delicate, and then they depend on seeing through the camera, which is the trainee is holding. So you can imagine that, okay, if the trainee tries to move it or drop the camera, then the surgeon's gonna let the trainee know that that is terrible. You cannot do that. I'm doing a procedure here. Why did you move the camera? And typically, because I'm tired, is usually not a good option. So, hopefully that illustrates kind of the unique challenges in the surgical occupation. Trying to highlight the risk is that their postures are relatively poor. They have a lot of these kind of either hands are lifted up, they have to bend over, twist, leaned. So in terms of ergonomics, not the best. We also kind of highlight that there's a lot of constraints there that puts them in those postures for very long periods of time. That raises their injury risk. So what are some solutions that we can do to help prevent them? So many different ways in occupation that you could provide some interventions or help to prevent injuries. First one is organizational. That is not my area of specialties, but I'm sure our friends in management have some ideas on how to change kind of company culture and do a lot of more administrative stuff. That's an option, but typically it's very hard. I think especially for healthcare, it's one of those cultures that are quite challenging to kind of change how they do things. Actually, most workplace cultures, it's hard to change how they do things. Other things is typically, if I'm manufacturing a car, I could change the environment. I could rotate things, lift things, because it's an assembly line. I could have some flexibility there. The problem with the surgery is that the thing you're trying to rotate and reposition is the patient. So you can imagine if you are putting, let's say, I want the patient kind of my shoulder level and tilted sideways. Probably not because of patient safety reasons. Still, even though we care about the workers in a healthcare setting, a lot of times and most times, I think patients comes first. So that's not an option. Administrative, we talked about breaks, taking breaks. Our nurses in the US, very good at that. When they have time clock, they clock out and they get substitute. However, that's kind of ability is not available for our surgeons and surgeon trainees because, again, they're the ones that are trying to finish up the procedures. And the nurse, they typically provide a supporting role, so they're able to do rotation. We do a lot of this too here, and I'm sure a lot of people in medical technologies is trying to develop new devices. Not just new devices on how they perform things, but how the better ergonomics, better usability. That's, again, a very good area. Another area is another topic of research in medical technologies is robotic technology, robotic assistance. Our team is doing that too. But while these technologies, while these new tools are being developed, getting tested, getting regulatory approval. That takes quite a bit of time. We need some interventions that will work now, and that's why we arrived to exoskeletons. So exoskeletons in general, exoskeletons aren't very new. Exoskeletons been along for a very, very long time. In that, in the past, you could think of it, for example, the military have these powered exoskeletons that really augments people's capabilities. The problem with the powered exoskeletons, and of course also in rehabilitation, there's a lot of powered exoskeletons in rehabilitation. One of the key problems with those exoskeletons in trying to use them for the workplace is that they're relatively more expensive and a lot more things involved. When you're working for a company with thousands of workers, you can't really implement thousands of powered, expensive exoskeletons. The innovation here is that they became passive. Basically, no longer do you need to have battery power. You don't need to have really anything. It's all mechanical. It's just a spring, basically. And the spring is, when you put a load on the spring will provide the reaction force and help support some of the load. This makes it much cheaper. You don't have to recharge it, easier to maintain. So that's why it's been picking up a lot in occupational settings, in jobs that require people to work under, in situations they probably shouldn't. This is a kind of an intervention or protective equipment to help them do the job anyways, passive exoskeletons. The unique areas that I work on is looking at exoskeletons in healthcare, but there's been already a lot of work in exoskeletons in other industries. Here you can see automotive, manufacturing, very key early adopters of exoskeletons. And exoskeletons have many different forms and features. I would kind of argue that you could probably find an exoskeletons for almost any body part, but the most common ones are supporting the back. So when you're lifting, it provides some spring for you to lift the load a little bit easier. It could be on the shoulder, which is what we're going to show today, where you help support kind of more overhead work or your arms being held up a little bit higher. I guess for this exoskeleton, the one here on the right side, the orange-black one, interesting question is that what did you think it was originally designed for? Or what job do you think that exoskeleton was originally designed for? It's supporting the arms. You can see this in an automotive manufacturing. A clue here is that it's actually not originally designed or intended for manufacturing. It was actually originally designed for surgeons because they saw that the surgeons were using those postures. Obviously, as a business, they saw a bigger market for industry versus surgeons. Not too many surgeons, so when you see not too many surgeons, not a lot of opportunity to sell. So it really picked up in automotive. In the next couple minutes, so the couple questions then. So you have some interventions. We know we have a lot of problems. How can we make them work? Or do they work? That's the biggest question. Can exoskeletons help surgeons perform better and be able to perform without hurting themselves? There's two steps that we've approached, and this is very typical for human subject research or human factors research, is first you identify, based on kind of usability testing, what is the perceptions, what are some problems, what are some of the things you have to do to make this technology be accessible in the workplace. And then the second part is one of my favorites is let's go into the operating room, let's go into the field, the workplace, and let's try and collect data and see if it actually works. So the first study, I'm going to go a little bit quicker, is more on the early stages of getting this from kind of a product to getting it into the operating room. The first one is the focus groups where we talk to a lot of the people. So basically focus groups is interviews, really. And you're talking with the people that are working in the OR. We have experience in the OR, but we personally don't have experience what it's like actually working in the OR, working in the system. So it's very critical to ask the workers and interview the workers unstructuredly on, what are some of the things that are that this could be benefit, this exoskeleton can benefit, and what are some of the things that we need to fix in order to actually work in the operating room or in the healthcare. We also assess whether they'll interfere to their jobs. I guess that's the most important questions that they'll ask, is that if I'm wearing this exoskeleton, will it affect how I do my work? In this case, because it's surgery, they're very key on this because If it makes it more difficult and it affects the patient outcomes, I would say anybody who asks within the entire health system would probably say no to your device. And just some high overview is that in order to do the focus groups, we had them try things out first, try them out as in actually wearing devices, and also trying it out as using it in a simulation task. For the focus groups, this is just your very typical qualitative research. You have moderators, you have questions, and you collect data on that. And then I'm going to zoom forward because I want to focus on what happens when we put this in the OR. But from the focus groups, we could find that there's a couple themes that they recommend that you have to consider in order to implement exoskeletons to the workplace. Things like individual characteristics, what the benefits and return is on the exoskeletons, environmental and social factors, and also intervention characteristics. Things like, what are some of the logistics? Are you going to get one exoskeleton for everybody, or is this something that they could rotate around and use for multiple individuals in the team? The second thing that we talked about in the usability is the usability score. For this, after they tried it, they filled out a survey, a questionnaire. And from that questionnaire, this survey score kind of gives us a number. And based on that number, let's just say that whether this usability is okay, adequate, or excellent. In this case, the interpretation of this number is okay to good range. All right, so this is the meat of the, so we did our focus group, and we did our simulation testing. We found that usability is okay. We found some problems that we can address, or some ways that addressing how to put exoskeletons in the OR. Now we're ready to test this in the workplace. Let's go live. Let's put this on the surgeons. Let's put this on surgeons while they're performing procedures on patients. Specifically, actually, we actually have most of this on the assistants because, like we said, they're the ones that are holding these static positions in non-optimal positioning across the surgical, across the bedside. So just a key thing that I'll talk about later, all our participants, they're right-handed. What we did was that we followed these participants. We went into the procedure. Sometimes when we watched them, they did not have the exoskeletons on. Sometimes when we go, they did put on the exoskeletons. And then we collect a lot of data. Some of the data we collected include measurements of how some of those biomechanical factors I mentioned, in that how much muscle exertion, how much muscle force and fatigue that's being exerted, and also how's the ergonomics. Did it affect the ergonomics for the better? Those are EMGs and IMUs. So IMUs, this is a little bit more technical, but IMUs are basically accelerometers. Most of our watches, our cell phones, we have an accelerometer. These things are great because they're relatively small, low cost relatively, and it lets us know positioning. To make it let us to have the accelerometers tell us about the body positioning and biomechanics, basically we do a couple of transformations. We take the raw data from the accelerometer, process it into angles, process it into body segment angles, and then put them together to understand what is the posture, what is the neck posture, what is the back, and what is the shoulder posture. The second thing is EMG. The EMG technology, it's basically when we tell the muscles to contract, it's usually electrical signals. And also, a lot of that electrical signals we can pick up by using sensors that are taped onto the surface of the skin. For this to make it to let the EMGs or give us some information on the muscle fatigue and exertion, what we do is that we take those signals collected from the sensor, the EMG sensor, we process it, we filter it, and then we extract information on what's the amplitude and what's the frequency. One thing to note is that for EMGs, because it's detecting electrical activities from the muscles, everybody is different. Their signals would be slightly different characteristics, could be higher, could be less. What we do to calibrate and normalize across the population, we use a technique called maximum voluntary contraction. Basically, at the beginning, we tell the participants to go, their strongest possible, and we take that measurement and we normalize all the rest of the measurements using that strongest. I'm going to skip this one really quickly and then go straight to the results. So we took some surveys, and looking at people before and after the exoskeletons, we actually saw, based on what they tell us through the surveys, they felt that the exoskeletons didn't really have much impact. Looking at just the bars, there's some differences, but because statistical significance, you need to have either large sample size are small variations. We didn't see statistically there's any significance. But that's why we use sensors, because the sensors tell us exactly what their posture is, tell us exactly how much force their muscles are using, and here, this is where we do see significance. So just to contrast, surveys is after they use the exoskeletons, they tell us, how you're feeling. The problems with that is somewhat very subjective usually, and also might depend on the day. But the sensors doesn't really have that limitation, and it's a little bit more objective. Specifically for the sensor, we see that not a lot of difference in terms of posture. Here, this measure is basically we took all the posture measurements and we summarized it into how demanding were your postures, and we saw that the exoskeletons reduced demand for the right shoulder. Looking into the EMGs, or the muscle activity, we saw that muscle activity actually reduced across the board for the left trapezius. So these are the EMG measures. Similarly, we also saw for the right is that we reduced the deltoid on the right. However, we saw that the right side here actually has lowered, the blue bar during the exoskeletons. What that measure means is that people are actually experiencing more fatigue. It's not statistically significant, but it's large enough difference to make us kind of somewhat concerned. And the key things here is that why would people be more fatigued when using the exoskeletons? Any guesses? I guess I shouldn't ask that because I already have the answers on those bullet points. But it's because it's a spring. And sure, it supports the body position when you need it to be up here, but when you're doing a surgery, your body is moving everywhere. So when you're not needing the support and you want to operate, let's say your arms on the side, you actually now have to actively resist that spring. And that active resistance actually caused potentially a little bit more discomfort, a little bit more energy expenditure. So to conclude, and to wrap it all the way to the beginning, what are some of our future work? So if you remember, in the beginning, I talked about being able to stream data in real time on what the person's state is, cognitively, physically. We could get that information now in real time, and we could actually process it to classify things. What if we merge the two in that, can we make these exoskeletons smarter based on what we sense from the surgeons, what we sense from the user, and then feed it back in? All right, so with that, I'd love to give some acknowledgments. Thank you everybody here for attending this talk. Thank you for the collaborators that we had. And of course, a lot of this work would not have been possible without the help of our large study team, both from the medical side, the engineering side, and also from some of our exoskeletons experts. Thank you.
Okay, I think we have room for one question till we move on to the next lecture. Is there any question from the audience?
To be honest, I do not really understand how this works. What kind of movements does it support, so to say? How do you control this, what it supports? Can you give us a bit more insight?
Yeah, this is a great question. So in industry, we saw the person working overhead. So it supports the body in kind of bad postures. But in surgery, we thought it was especially important because we said that the surgeon must hold it for a very, very long time. So in that case, it just supports the hands kind of continuously in this motion. So you could think of it as, I could put my hand up here and I could lift the weight here. I could probably only do this for 2 minutes. I don't work out. So only 2 minutes. But if I have an exoskeleton, I could probably do this for maybe 30, an hour, 45 minutes because it supports that so I don't have to use my own muscle. So that's what the exoskeleton does, is that it supports this position. It's actually not moving too much. There might be a little bit of movement. But you could also think of that if it's supporting here, if I move it closer here, then I have to kind of push down on it. So that's why we saw that in the end, there's a little bit, some problems with that people didn't really like. And that when they don't need to do this, then they have to force themselves down, or at least use muscle the other way.
Thanks a lot.
No, thank you.